Welcome, everybody. This is Trends in AI for 2025 based on the latest NeurIPS, or as we call it, 12 Days of NeurIPS, Day 2. So as I mentioned, we're going to start investigating or diving deeper into one of these 12 areas. Today is what is happening with agents. Okay, so we're recording everything for those of you who cannot make it. And again, the plan is to make a podcast out of it. So agents. I think the interesting fact, which I wasn't expecting, is that LSTM is back. So as we mentioned in the first talk, LSTM pioneered the sequence-to-sequence modeling. It was invented in '93, but it only became popular in, I think, 2015, basically, which actually happened to be 2014. It won the Test of Time award. Now, you see the strawberry here. So the strawberry is the O1 OpenAI reasoning model. And since everything is moving towards test time compute, so investing more time in reasoning, we need language models that they are not necessarily the best when we measure the performance in token generation, but they're extremely fast. And because we're going to call them multiple times. So here, again, that comes from the talk from of Hochreiter, who is the inventor of LSTM, was a keynote towards industrial artificial intelligence. They compared the LSTM with Mamba and Decision Transformer in some robotic tasks and things in biomedicine and vision. I don't think it's a comprehensive. You can go to the paper. I have a reference to the paper. Because you see, I see a transformer here that's only 200 million, and this 102 million. We're going to see how it behaves with bigger, with larger number of parameters. But it's definitely interesting that now we know how to scale LSTM so that we can train it. Here's the paper on. You can make a 7 billion LSTM. And you can see that it does better than other transformers that they are bigger. Okay, these are 7 billion, and actually bigger here doesn't necessarily because they have the same number of parameters, but they have been trained on larger number of tokens. Anyway, I think it's remarkable that it is where it is because there's still Gemma that does better, or Zamba and DCLM, but it's in the ballpark. Okay, it's a first attempt. And notice Qwen. Qwen is the Alibaba one related to DeepSeek. It's quite good. But anyway, it's pretty good. And what is really interesting, for those of you who don't know, transformer has kind of like a quadratic complexity. It really depends on how you implement the attention. It can be less than that. But the problem is that as the context, the pre-fill increases, the token per second generation of transformer goes down. So the throughput goes down. But XLSTM and Mamba, first of all, I want to say that they're both under the same category of dynamical systems implementation. They share some common principles. You can tell that you can feel the context, and the throughput stays stable, the same. So that's a really good property to have, especially when you're looking to commercialize things and you want things to be stable. So as I said over here, XLSTM is die hard, and here are some kind of advantages and disadvantages. Transformers are quadratic in context length. Only pairwise, uses only pairwise interactions via dot product. No complex interactions, no abstractions. Sorry. Okay. And I think that's what it's interesting here. The LSTM has stood the test of time, and here are some LSTM limitations that LSTM used to have, and the X-LSTM has addressed. So, in my opinion, this is interesting that if you compare it like Hochreiter and Hinton, that they had some parallel paths in AI, of course, contributing both to the breakthroughs that we see now. They've all been very diligent and very patient, and revisiting and learning from their from their mistakes. And this is an idea that is, I don't know what is 32 years old now, and people, they don't give up without being necessarily, counterproductive over here. So we've seen several ideas coming back and forth, and one learning from the other. So I think it's something that it's worth noting. Here's an oral presentation. The agent board, again, one of the problems right now is we're trying to solve some very complicated tasks. And, you get a new language model. We have business decision makers that they have to decide what they need to buy or what they need to use, engineers. And, it's not like for databases, we have TPC aids, or, there's other benchmarks that are very, they represent really well. I mean, a benchmark never represents the full experience, but it's a good indication of something good or bad, and something that we don't really have for agents. So I think it's a great framework here, agent board, that offers different metrics. And I think the authors here, what they introduce is the progress rate. As you can tell, here's an agent trying to put a clean ball in the fridge. And, obviously the success rate is 0 until you put it. But even if the agent gets blocked over here, the fact that it did 75% of the job, it's something that, makes it better than an agent who stopped at 30% of the job. It might be, maybe that means that if you try again and again, you have a higher chance to achieve that. Also, something else that I wanted to notice, that this is a task performed on a symbolic simulator. I don't know the details, but this could have been a simulator learned from YouTube videos. So you can say, I have a kitchen. Here's the, draw me a kitchen where here's the bowl, here's the sink. You give the setup, and then you have a bot that is trying, a robot, to put that, interacting with that world model, and you're saying, now I moved it from here to there, and then it updates the simulator, and it tells you if you're doing it right or wrong. And of course, the agents are also very useful in other tasks. A website is another simulation engine where you want to buy a women's fur leather jacket. And here, of course, it's, it found everything. So it has a progress rate 75% because it's about to buy a jacket that is fur leather, but it's not for women. And, there's, the paper talks about how to, how do you define the progress rate? Because you need to find states, and sometimes you're not exactly in that state, but close to that state. But there's some interesting, statistics that they gathered. First of all, you see it's a very comprehensive benchmark. They do have the DeepSeek, the 67B. I think that's the one that was, it's not the R1, that was supposed to be the agentic one. But anyway, these are kind of like the main results. And one of the things that they wanted to show over here is that they kind of like wanted to explain what I said before, that all these models have more or less the same success rate, which is pretty low, but there is a big difference in their progress rate. Okay, so I think that's what they want to motivate. There is also something else that you can do, which is called agent tuning. So you can tune your agent, and that basically tends to give better results. And I think it's probably what they are comparing these models, that they are they've done tuning. I don't know what's the difference between agent LM with XLAM. Anyway, you can find the details on the paper. So sorry, we need to mute someone here.
Thanks.
Okay, Babis, I think Labis, you need to unmute yourself. Yes, that's okay. So, and then there's this other example, I think, yes, now I get it, where strong coding skills, so can, you know, can have a better, can make a better agents. So if you train them with code. And the other is that proprietary models outperform open weight ones. So GPT-4 and Claude and Gemini, of course, we've been now to Gemini 2. They seem to do much better job in the benchmarks that they did. And this is another interesting metric. So, you know, this is a very interesting curve, in my opinion. And this represents what people call well-balanced language models. Okay, so, and this is kind of something that I was pointing as a mistake when people were evaluating the DeepSeek R1. Said, yes, it's great for reasoning, but an LLM does not only do reasoning, they do instruction following, they need to have empathy. There's a bunch of other properties that the language model needs to have in order to be general. Okay, like think about a human, where someone is very good at talking to people, someone is very good at doing math, and somebody is good at everything. They draw that line between Mistral Turbo 3.5 and GPT-4, and basically that's what they're showing you. So these are all language models that when it comes to evaluating when they're measured on MMLU, which is a metric that has to do with next token generation tasks, all of them are about the same metric, But when you look at the progress rate, Da Vinci 003, which is actually a bad model, or DeepSeek 67B, or 3.5 Turbo is doing much better. And I just kind of noticed that these are some smaller models, like this is an 8 billion, and maybe it's very good at MLU, but it's again not a well-balanced model because it's not close to that curve, and it doesn't do well on agentic tasks. Now, I think what the point that the paper wants to make is that these are the three attributes that they make that your language model needs to have in order to be a good agent. It needs to have the ability to decompose, ability to ground, and ability to long self-reflect. The term long is very important here. And here are the takeaways. LLM agents are complex systems that involve multiple abilities. Improving each ability is necessary for building good LLM agents. We need to perform analytical benchmarking of its various abilities to interpret whether the agent is good or why it works badly. Evaluating the process is as important as evaluating the final result. So Agent Board aspires to be that framework. This is next. We have this great tutorial. We spoke about that yesterday a little bit. It says beyond decoding, meta generation algorithms for language models. And here I managed to also find get tutorial slides and some other references. You can see more later too. So as I mentioned yesterday, when we're talking about the agents on the micro level, this is equivalent to talking about meta generation. And if you prefer to read, there's an extensive tutorial, like the same tutorial. There's a paper which is quite lengthy. If you want to go and see that. Now, the tutorial obviously goes to the road. How we ended up using meta generation. So we talked about that yesterday. We've kind of like exhausted the resources for pre-training, and here are some first indications. So AI achieves civil medal standing of solving International Mathematical Olympiad. I think this is the Alpha Math, if I remember. That's from DeepMind. And this is from Databricks. where kind of like talks about, I think it comes from a text to SQL paper, and on a high level, meta generators, high level strategies for calling generators and using external information. So this is kind of like a diagram. We're going to see it in detail. We generate more to improve task performance. This is the chain of thoughts. Combine multiple models, verifiers, retrievers. So that's also part of the agentic stack. And incorporate external tools, information, and feedback. And that refers to the case where you have to go do web search. So when you do meta generation, you might want to use extra tools that they take you out of your ecosystem. I think this is the point where you go from what I call micro agent to a macro agent, where you basically, because when you go to the web, now you have another agent that is responsible for reading and understanding the web. And here's like a very simple example from the chain of thought paper where you have an input and answer, and if you put some thought, you get a better answer. Now, the simplest form of doing meta generation is calling yourself again and again. And if you happen to have a verifier, you just stop when you hit the right answer. And the more times you can sample, the better results. And here's a deeper dive on what we saw yesterday. When you focus on the decoding, most of the language models, what they do is they do greedy decoding. Taylor Swift, 4713, 1989 is N, and the next, the token with the highest probability is American. But as you can see, there's a whole tree over here of choices that you can make. And here's the same thing with the probabilities. So, if you try to do greedy, you basically follow, here you take the top two, 0.13, 0.06, and you follow this. You see where you are ending up. Here you join, you end up in something that has probability 0.0008, and this one has the same probability. What I'm trying to point here, and I'm not intending to spend more time, you can see the result, is that picking the path with the highest probability is not necessarily the best solution. So, for example, the greedy solution says Taylor Swift is a former contestant on, and that has probability 0.0004. If you do a non-greedy and do search, it says Taylor Swift is a singer, comma, song, and that has a higher probability, but it's incoherent. And it turns out that this is called MAP, maximum posteriori probability decoding, works well for closed-ended tasks like translation or question answering. So that's a strategy which is, it has specific uses. Now, in general, you might have cases where your decoding is constrained. So embedding LLMs, for example, in the larger systems requires that they can communicate with larger system, example, JSON. Okay, so how do we force LLMs to generate JSON? So we basically take the JSON grammar and we build the automata, and that kind of like you apply this constraint, this automaton, by it's basically tweaking the probabilities when you decode. So your decoding takes, there is here it says anti-expert, but it's something different here. So when you're getting the next token generation, you're somehow weighting your probability based on the probability of being in that grammar. Okay, and of course, the way that you control this probability, sometimes you see it if you're using Together. I think this is from Together AI or from OpenAI, I don't remember. These are the parameters that they kind of affect how you do that decoding. Like, are you doing beam? Are you trying to find the top 5 and how deep you go before you make an answer? And of course, this is kind of like the simple strategy. You can call that a very simple agent. But there's more refined strategies like tree search, chained, parallel refinement. Okay, that you can use. Yeah, sorry. We need someone to mute here. Can someone, Randy? I think we need to mute you. I don't have. If anyone has access to mute people, to try to mute. Okay, thanks. Here, in some cases, what people would do is, okay, try to sample as many times. And if you have a verifier, you pick the one that it says it's correct. But sometimes you don't have a verifier. And what happens is you do some kind of voting. So if you sampled it 1,000 times and the result of this math expression was 60% 5, you're saying, oh, okay, probably 5 is the correct one because most of them are leading me there. It's a good heuristic. I mean, as we know in math, that's not the way that you do things with statistics. But there are some ways of doing weighted voting, and that can improve the results. Another example that you might have seen that, especially if you use image generators, which says rewrite input before generating. Weston calls that the system 2, or sketch a proof. If you ever try to use DALI, you will realize that you ask for something and it rewrites that and then it does it. Yeah, you can find, there's the AlphaVero system. There's, unfortunately, I'm trying to keep things kind of tight in time. There is something interesting where sometimes you might not necessarily have a verifier, but you can have, you can take two outputs and that one is better than the other. And probably, this one is checking for profanity. And you can have like some keywords that say, oh, okay, I found less profanity keywords here than this one. So that's probably a better one. So all sorts of tricks. And, of course, the biggest question is, and the paper goes, the tutorials in the detail, I'm designing a system with agents. How do we choose a meta generator? The first question is, do I need a small or a large model? A small model with more generation or a large model with fewer generations. We've seen this example so many times in engineering, like when you do optimization, do I need to do long steps but few of them, or smaller steps but too many? Stochastic gradient descent, for example. And this experiment fixed strategy and vary model size and number of tokens, and you get these curves that they talk about. What is compute optimal? These are the points of compute optimal, but you also evaluate the test error on this specific benchmark. And the second question is, what is the compute optimal meta generation strategy? And then obviously, once you find your model size, then you experiment with chain of thought, tree search, reflection, whatever. Now, what I don't know, and I didn't find this benchmark, is that can reinforcement learning fine-tuning automate this search? So I don't know when you're doing reinforcement learning if some of these parameters are learned, are relevant. It's kind of interesting. And that kind of concludes that tutorial. Now, what was interesting is that we start seeing, that's what I've been saying, that NeurIPS is a great conference even for the industry, because we see we've reached a point where the big companies or the different initiatives, sometimes not companies, they're coming up with programming stacks, so Microsoft here has their agent stack that, again, it's on a programming level. They call it AutoGen. And we've actually used it here at Relational AI with Agapi in our paper. And here's the GitHub. You can find lots of tutorials. They basically work on what I call the macro agents, where the each language model needs to do one task, and they talk to each other, and they need to be synchronized. And here you see kind of like a software team trying to resolve a bug, or this is kind of like a company. So kind of like the vision is that in the future there's going to be agents at different levels. The way that you have a company and you have the CEO, the board, the executives, the different departments, all the way to technical work. This is the macro level, and of course, as a company, the company doesn't meet in one meeting they make a product. They do a lot of refinement. Okay, so I think what you should, and they have this Magenting one team. That's an example. What you can take from this. I think it was an expo. Yes, it was an expo. The 1 hour talk is the programming model that they're using. Now, that was an interesting talk. It's called Active Trading, Building Agentic Apps with Llama 3.2 and Llama Stack. They talked more about the language model and less about the programming model. And that kind of shows you that when people talk about agents, sometimes they mean different things. And they talked more about how they trained, they crafted Llama, the data challenges, the general strategy, the distillation process. Of course, all this has to do with general language models, not necessarily for language models for agents. And now when they talk about agents, they basically say that you can do function calls, you can use JSON input output. They're low latency. It's kind of strange because I think it really depends. So probably large and latency is something that people would prefer in agents. But anyway, it doesn't matter. They kind of like tested it on some arena over here, like a leaderboard that they scored first. This is interesting because I think regardless of agent, again, I put this talk in the agent section because that's how they wanted the messaging to be. But this is a useful talk that basically tells you which model to pick based on the use cases and what they recommend. I think it's very useful. And again, something that I really appreciated is that they basically tell you what they heard from the customers and basically the developers. And they said solutions to get started faster, flexibility to customize models, maintain control over data, build applications reliably and safely. And these are the providers, probably the people who offer Llama, I don't know, like Snowflake Together and others. Standards to build toward bespoke tooling for interoperability, codified best practices for serving newer Llama models. And, we learned on our experience. So basically they tell you their, what they heard and what they did. And here's kind of like their stack. And they talk about the agentic app development APIs. And so these are the part of the agentic stack. And this is part of the, model development API. Now, if you see, when they talk about up next in Llama stack is harness to run agent evals. That's what like AutoGen does. UI for playground and human feedback on evals. So what I'm trying to say is that this talk mostly about what they've done with Llama, and I think they felt the need that they need to be in that arena and have something to say. So I think the takeaway from this talk is that what is coming up next. So Llama, I don't think is really geared around agent as it is. It's a general purpose language model. But I think if they add these things that they're coming up, it would be an excellent addition. Now, it's no secret that we humans like playing games, and animals too. And the games is how we learn. Okay, there's been a study that says the dogs are playing not just for fun, but because they're getting ready to learn how to hunt. Okay, so it's gaming is a learning process. The learning process for us is a learning process for language models. And this was, again, an invited talk in the language gamification workshop, which I really enjoyed. And I want to stand into this motivational, slides. So basically, you're playing tic-tac-toe, and it takes 33 seconds, and it gives you an answer. And then there was another motivation about what happened in chess, where you can't see it. I can increase the font, but I can read it for you. It's basically modern LLMs are trained on a sizable fraction of all the text ever created, but now you can also design. They weren't designed to be good at chess, but however, if you train them on chess games, so if you add them, they can become pretty good players. And I want to dive into some details. So this is a data set of chess games. And this is human played games obtained on this platform, annotated by Stockfish, and these are other generated and annotating by expert engines. I think Stockfish is actually as a model. Yes, that's why you see that it's much bigger than the other one. So these were basically, yes, random chess games or chess game played by a platform and then annotated by language model. Long story short is that what can happen now, you can take games and you can encode them as text, and then you can basically say what's the next possible action. The story here is that this now, you can take a language model and make it a very good, a simulator, like a model that if you try to play a game, a move, it will know if that was a valid move or not. And it can play back with you. It can do a pretty good move. And what is interesting in this picture is that the state-of-the-art chess engine, they basically tried tens of millions of moves, like the Deep Blue, before they try them and they score them and then they pick the best. Now AlphaZero, that's using reinforcement learning, it's playing about 10,000 moves in the horizon before making a move. Like a human grandmaster makes a few of 100 moves in his brain. And that's how the LLMs are working. They basically generate, they're more close to what a human does. And then there are two ways to play chess. One is with internal search, where you have a single model, no external search loop, and it does an internal minimax search. It linearizes the trees into a text format, runs supervised fine-tuning. Okay, so basically what happens is the model learns how to create these trees and decide. So this is what we call imitation learning. And this is the reinforcement learning, where there's an external controller where you have your LLM generate, and it does an evaluation, accepts or rejects. So the verifier is an external verifier. It can be a language model. Okay, what you need to keep is that this is reinforcement learning and this is imitation learning. And if you remember from yesterday, when we discussed about DeepSeek, we said that it looks like that what DeepSeek did, it did some imitation learning. So it got some high quality data played from or generated by, let's say, OpenAI, and it got kickstarted and then used reinforcement learning to learn how to work better. And that's something that the researchers here can verify. And here's the conclusions and future work. A single transformer can act as a strong word model, like chessboard, value function, you can evaluate if it's good, for multiple games. Asynchronous external MCTS, I don't remember what MCTS means, but it's basically an external verifier, scales gracefully with compute resources and actually reaches grandmaster level. Okay, internal search can distill search trees into a single model call. And future work, language explanation, strategic analysis, basically exposing to you the chain of thoughts. Might get a little bit out of time, hopefully not. Now, here's a mind-boggling paper. It was an oral. So your kid wants to learn how to play soccer, okay? You as a parent say, okay, take this ball, go with the other kids and start playing. It doesn't matter, just kick it, look what the others are doing and try to do the same thing. And you will, when you score a goal or when you deflect an attack, it means you did something well. You're going to get a hooray from your team. Now it means you learned. Okay, this is, or maybe we send you play with a team that they, teach you in practice. So this is reinforcement learning, trial and error. But you would never tell your kid, oh, you really want to learn how to play soccer? Go and read a book about soccer, about the rules, regulations, and about great players and great games. That sounds like really, I mean, I want to say dumb. Not really, okay? Because language models can actually learn how to play soccer by reading a book, okay? And you should watch that presentation. It's really fun. And the way that it works is, if you just read the book and you go and you play, what happens, the play is very boring. I mean, it learns how to, from the rules, you learn how to, you don't lose and you don't win. That was the problem. The game wasn't moving. It was making valid moves. It was holding the ball, but it wasn't doing anything, fantastic. And they solved the problem because they asked the language model to imagine a game, okay, based on the rules. And after it imagined the games, now you go and you play them. You go and you train your policy network to do that. Okay. So basically, it's equivalent of saying, oh, you want to learn how to play soccer? Go learn the rules, read books about what's going on with soccer, how it's good practice to play, but all the theory. And then imagine games, like go spend some time imagining games, and then go and play with your friends, and you're going to be pretty good. Now, surprisingly, for those, I don't know if we have any long distance runners in the audience, but this is something that a lot of athletes do. Like they train their mind and they can push the barriers to run faster and break the records. I don't know if it's really related to how language models are thinking, but there's some kind of analogy here. And the point is that you know you can apply that to other things. People tried that in the past, teaching a language model, but with much weaker language models, giving it the manual of SQL Server and ask it to go and tune a database, learn how to tune it. But they didn't do it as sophisticated as this one. So you can imagine right now giving manuals to language models, and then they go through this interesting reinforcement learning process, and they learn how to fill a task. And here's some interesting references. And that wouldn't have been possible if Google hadn't created, they call it football, we call it soccer generator. Again, this is, there's a lots of papers that they talk about different ways of, they're all agentic ways of thinking. Whether it's a chain of thought here, they call it decompose, analyze, and rethink, solving intricate problems with human-like reasoning cycles. And you can see, here the results. I want to try to keep it, I promise I'll keep it to 45 minutes. I'm probably going to be a little bit late, but you get the idea. Okay, you can read the slides on your own or the paper, but this is something that you do as humans. And this paper has more like a theoretical interest, because it turns out there's a limit on how far you can go with chain of thought. Okay, so even if we think about big discoveries in humanity that didn't happen, it wasn't like Einstein thinking for 10 hours, one chain after the other. There's this aha moment. There's a bit of art, where you take a completely different direction, serendipity and other stuff. So I think the model tells you how far you can go with chain of thought. And now we're moving a little bit outwards to what I called macro agentic systems. And there's some really fantastic papers. Papers that I think they reveal the beauty of Gen AI in the real world, in the world of enterprise and the world of science. So this is a paper, I want to say it's from MIT and Google, where it's basically a group of doctors trying to make a medical decision. Sorry, it's called MD agents, and again, you kind of recognize different synergies of agents. And trying to make a decision. Again, it's a great paper. And I think it's not as simple. What you see over here is that it's not just like a policy. You talk first, I talk second, and talk. But the dynamics change interactively. How people, like, who talks to whom, it's being decided. So this is what I call like meta agents. Like, okay, where it's not as simple as I just described the protocol. And then I think Stanford also had a very nice. I think that's a Nature paper, and you can find it as a talk on the math AI. Surprisingly, this is a math AI talk. Again, math AI is more than math in this conference, and they basically created a virtual lab of biomedical scientists where they do they decide how to create the agents, then they have team meetings, individual meetings, and AI agents design new SARS-CoV-2 nanobodies with experimental validation, and generative AI for designing and validating easily synthesizable. Notice the easily. I'll talk about that. Structurally novel antibiotics. I mean, imagine this is going to be your company one day. I don't know if it's going to be the company of our kids. It might be the company of our time. I don't know how some things are happening. But what is really interesting, I mean, just to see the level of the detail. So this talks about how they build the antibiotics. And, antibodies are kind of easy because they are proteins. And I'm saying it's easy because for proteins, the reason why, I don't know if you know, the reason why I learned that recently we love proteins is that once you design it, there's a factory, I think it's called ribosomes, I'm not sure, but nature, if you provide the sequence, knows how to construct that. We have a way to manufacture it at scale. But when you in antibiotics, they are like general chemical substances. And yes, it can design a molecule which is correct, but you go to a chemist and says, that's fantastic, but I'm sorry, I don't really know how to manufacture it. So the system here wasn't only able to design the right one, but it was also to design the manufacturing process. Like, first you build that part and you do this other interaction, and you do that, which I think it's fantastic. By the way, that whole thing was inspired. This is a great book that I recommend. I've read it. It's called a happened personal story to be a victim of a very nasty bacterial infection, and that talks about a scientist who her husband got a really resistant bacteria from a nice cruise in Egypt, and how she actually used active science, active research to fight that. Anyway. And of course, here I just want to take a moment to talk a little bit about our work here at Relational AI. We use the same process with a set of agents trying to tidy up databases. We call it schema refinement. We can talk about more at a different time. This paper basically talks about automated design of agentic systems. So these are agents that they are trying to design other agents. Very interesting. This is, you kind of like, they use some evolutionary strategies, or they brute force, they try different techniques, and a paper that I liked here again. And I don't have time to talk more about that, but I'm just going to make a stop. This is an interesting talk. It describes the process that OpenAI, as I mentioned, OpenAI has two talks about agents. This one and another one about how they, they used games to design Strawberry. It's a different talk. Yeah, this is another one, how they competed on the international Olympiad of Informatics. And I'm gonna stop here. Next time, I'm just giving you a clue. It's gonna be language models for tables. And I'm gonna stop